Welcome to Lesson 3, Video 1. We're going to be talking about the assumptions for linear model and residuals. This is found on page 130 and 136 in your course pack. This is what it looks like. Hey, there's my finger. Remember, our whole goal here is to develop a useful model so we can predict and make estimations and make decisions based on some data. In multiple regression, it's to build a probabilistic model that relates a dependent variable, let's call it the explanatory variable, to one or more predictor variables. Oftentimes, we'll have k predictors. So for example, if we're doing the size of a house, we might look at size, age, and number of rooms, and so k would be 3 because we have 3 predictor variables trying to predict the selling price of a house. And here's a general additive model. Looks very similar to what we had for the linear model. We just add epsilon, our error random variable, which has a mean of 0, and a constant standard deviation sigma. Our assumptions we make about epsilon, the error random variable, are pretty much the same. It follows a normal distribution, has a mean of 0. The standard deviation is constant. And we check the normality by probability plot of residuals. Has a mean of 0. We get that for free. We plot the residuals versus the explanatory variables, and we see if there's a random scatter about 0. Actually, that should be the explanatory variable, and see if there's no pattern. We can't really say it's mutually independent at various data points because there might be some relationship between the various predictors. Put that in your line, but the idea is that there's no pattern when you look at the residuals versus the explanatory variable. And we find the betas by minimizing the sum of the squares of the residuals. And you know you have this on your quiz. And you'll have this perhaps on a future test. And then we have what are called the normal equations to solve, just like we had before. So again, on page 130, we kind of go through this again. The basis of our diagnostics is residuals. Our residuals are given by our observed value yi minus the y hat I. And that's just your y hat. It's just plugging in all your x variables into the expression with the b's, and that will give you the residuals. There is only one residual for each data point, and the sign of the residual is positive if the data point is above the least squares plane, and then negative if the data point is below the plane. And we're talking about the vertical distances. So if you take a look, here's my little plane. This little observed y is below the plane for y hat. So in this case, the model overestimates here. My observed value is above, and so the model underestimates. So when we take a look at this residual for the blood-brain example, it turns out that our observed response was negative 3.568. Our predicted value was this negative 2.616. We got negative 0.052. So that our model overestimates the true response. Now just kind of think about that. Would it be best represented by this y or this y? Pause and make a guess. And the answer would be this part right here, because the y, the observed value, is below what your predicted value is in the plane. Let's go on to page 131. Again, the mean is always 0. And if you sum the squares of residuals, you get the sum of squared error. And this is what we want to minimize. Minimize the sum of squared error. And the sum of squares or residuals, or the residual error, is given by SSE here. And that's just taking the sum of all the residuals and square them. And we'll do this for the blood-brain example shortly. And then the total sum of squares is just like what you do in calculating the standard deviation, each yi minus its mean. And the total sum of squares is just some sort of variation, is how much variation is going on with our data points. And then finally, sum of squares regression is just like we had for the linear model. With a simple linear model, it's our predicted value, predicted minus our mean value. So let's take a look at what we could do if we did this in Minitab. Here I have the examples. Our response is log ratio, and I put all of these data points in, and I get out the linear model, and I can then look here for my sum of squares regression and my sum of square error. So the regression, sum of square regression, is right here, the 136.360. The error is 30.446, and the total is 166.806. So again, if I write these down here, for the sum of squared error, sum of squares regression, sum of squares total, you might sort of pause here and see if you can't recognize this from this data right here. But it turns out my sum of squared error is 30.446. My sum of squares regression is 136.360, and my sum of squares total, which if I add both of these up, I can see that it's 166.806 on my Minitab output. So both of these add together, and as you recall, if I take r squared, this will be sum of squares regression over sum of squares total. This gives me some measurement of the variation. And if I calculate that by the hand, I'm going to cheat by looking to see what r squared is on this. This will be 0.8175. So we would say that 81.75% of the variation in the y log ratio can be explained by a linear model in those predictor variables. So let's go to page 132 now. And we need to make one correction here on page 132. And that is, if this SS regression is a large part of the data, then large portion of SS total, it fits it well. On the other hand, the model will fit the data if SS regression is a small proportion of the SS total, while the SSE, this should actually be a large portion. And so again, this is how we get the sum of squares, or the coefficient of determination. And we did get r squared is equal 0.0817. Now, the one thing is that there's only one r squared for the entire model. Because we have so many variables, or so many predictor variables, we cannot kind of go one by one. And so we're not really going to have a little r correlation coefficient. So remember that we found the b's by solving the normal equations. And let's do another interpretation, kind of reviewing what the coefficient bi means. So for example, let's suppose we want to optimize some sort of solid state technology, and we have force, power, temperature, and time, and we want to know what the ball bond's shear strength is. And we've got some data, and it turns out that our beta naught hat, beta 1 hat, and beta 2 hats are all given there. The idea is that if you fix all the other variables and change that one in that coefficient, that's going to raise the explanatory value by a certain amount. So for example, if you keep beta 2, beta 3, and beta 4 all fixed, or at least the variables that go with that, and you change the x1 by 1, you're going to increase, by 1 degree, you're going to increase, I'm sorry, you should look at beta 3 here. Sorry, I was looking at beta 1. So if we increase the temperature by 1, we're going to increase the gram strength by 0.1297. And you do the same. If we increase the x1 by 1, we increase the bond strength by 0.217, and so forth. So for example, if we have this estimated equation, and we want to look at 35 grams, 75, 200 degrees in a time of 20 milliseconds, we get 38.41. But if we change the force to 36 grams, we would increase roughly the force by 0.2117, and so we would have 38.6 grams of force. So those coefficients are powerful when you interpret them. The other part is using predictor variables, where you can say, okay, we're going to use two types of vehicles cars and trucks. And we're going to let 1 be if the vehicle is a truck and 0 if the vehicle is a passenger car. And so we could look at the regression model this way. Now remember that x1 is either 1 or 0, so we could say, okay, if it's 0, then the mean time is beta naught plus beta 2 x2. And when it's a truck, we're going to have x1, and so beta 1 is going to be in there. Now beta 1 times 1 is 1, so we don't need to write x1 along with it. And so, in other words, it'll take, if we fix the mean time of distance held, then it'll take trucks longer to transverse. Just as a reminder, again, error residual sum of squares is SSE. The degrees of freedom is n minus k plus 1, and we'll mention some of this before. Now, the question will be, what predictors do we keep? And that will be in the next couple of lessons. The next video we'll talk about how do we use residual analysis and how can we estimate the constant standard deviation.